So thank you very much. I, as well, would like to thank the organizer and everyone here for being here, for also giving me the privilege to conclude this summer school with this talk. So in this talk, I'm going to give you a short overview of what we're doing in HCHIP, the Accelerator on a Chip International Program, in which our goal is actually to produce an accelerator, an electron accelerator, that would fit, say, aggressively on a chip, but perhaps less aggressively in a shoebox. That's the goal. And to do that, first, perhaps the obvious question would be, why do we propose using the electric-based laser accelerators? So for that, let's look at this table that compares conventional linear RF accelerators and laser-based electric accelerators. And the first thing that pops out is that both of these are limited by the breakdown of the material. So for RF accelerator, I could say that it's roughly 200 megavolts per meter, but we know that the electrics can withstand even up to 30 gigavolt per meter. So this is almost, or more or less, 2 orders of magnitude larger. Now, 2 orders of magnitude larger here directly implies that the maximum achievable acceleration gradient is also about 2 orders of magnitude larger. And this means that perhaps we can squeeze down and miniaturize accelerators by at least 2 orders of magnitude. Now, the other thing that you'd notice is that the drive period, here using femtosecond and about 2 micron laser, is roughly 5 femtoseconds, which means that we can get to large, very large peak fields. It also means, however, that on our structures for acceleration and other auxiliary structures would be much smaller in the order of sub-micron dimensions, assuming we're using subrelativistic electron beams. So in terms of applications, I will mention only one depicted here in this illustration. So let's suppose that you have a fiber laser that is fed through an endoscope and terminates with a small, very small enclosure, where inside you have the electric laser accelerator. In this way, you could produce high energy particles that perhaps could be used to irradiate a tumor inside a patient's body without disturbing healthy tissue around it. We could also think about other goals for this kind of accelerator, including X-ray generation and so on. Now, laser acceleration of particles, and in particular the electric laser acceleration, is not new. I think we perhaps could attribute it to this first publication, which is in fact a patent by Adolf Lohmann from 1963, in which he described several ways of producing and coupling light through diffractive and refractive schemes into a small channel or a gap where electrons propagate and subsequently accelerate. But that was a long time ago. Interest in this field only sparked around the 90s, probably because of advance in nanofabrication and high-energy lasers technology. And already in 2005, the group of Jamie Rosenzweig from Stanford suggested to use a thin metal sheet with tiny periodic slots in it, where light could be coupled in through the electric, where you'd then have a surface mode in this channel here. And if all conditions are correct, then an electron bunch that would go through here could be accelerated. More traditional photonic bandgap structures, such as this so-called woodpile structure, were also suggested. So here you could have your laser beam going inside this defect, together co-propagating with electrons. You match your velocities, and then you could potentially also get acceleration. But these days, what we usually do is work with diffractive schemes, where the goal is really to generate a mode that allows momentum transfer from the laser field to the electrons. And we would like and usually use the first order, because this is the most efficient one, unlike second order effects, which are most usually too inefficient to get high gradient acceleration. So in order to continue, let's just first discuss the common operation principle of all these structures, which is in fact the phase synchronous acceleration of particles. Let's suppose that you have, for example, a laser beam propagating in free space here from bottom to top, and an electron, let's say it's just one electron for now, propagating perpendicularly from left to right. Now, if the polarization of the laser is correct, then this electron would now experience accelerating forces and would accelerate. But half a period later, it would experience or feel more or less the same forces in the opposite direction, decelerate, and on average nothing would happen, no acceleration. If we could, however, and that's what we do, we modulate this laser field. So for example, here we're using a cross-section of a grating. Here, then, this grating has a period of lambda p. Now we can take the laser beam and in the near field decompose it in a Fourier series. Each term in this series is a different mode. Each mode has a different phase velocity, in this case c lambda p over m lambda. And if you match this phase velocity, for example, like I said earlier, of the dominant mode, the first mode, to the electron's velocity beta c, then we arrive at this very important synchronicity condition, beta equals lambda p over m lambda. So such that if this synchronicity condition is satisfied and the electron is injected into this field at the correct accelerating phase, then it would experience only acceleration and subsequently be accelerated. So in 2012, 2013, we've done this kind of proof of concept experiment in Erlangen. And here what you can see is you have the laser beam coming from here through single-sided grating made of fused silica with period roughly 600 nanometers. The laser beam goes from the bottom of this grating and through it and exits from the other side, producing the near fields. And at the same time, we have the electron beam going here perpendicularly. When it does get close to this grating, there is interaction, and some fraction of these electrons are accelerated. Once they're accelerated, they keep going. They go through a filter lens, which is a high-pass filtering energies, outpass filtering spectrometer for energies. Then through a deflection coil, and finally they go through a multi-channel plate, which allows us to see where the electrons hit, and because of this high-pass filter, we can also tell what their energy is. So here from these measurements, you can see, first of all, the acceleration fraction over the energy gain. So we use 2 peak fields for the lasers, for the one laser here. And you can see that we could reach up to 25 mega electron volts per meter acceleration gradient. Now we wanted to make sure that this is indeed an effect from the electric field, and thus we could just change the polarization of the electric field relative to the electron propagation direction and the grating vector. And of course, we expect that if we're not in the right polarization, we won't get as many electrons accelerated, as this is what we see here. This is a near field effect, which means that we have to be very close to the grating, and as soon as we move away from the grating, we're going to get a smaller number accelerated fraction, and this is what we see here. And lastly, we wanted to check the synchronicity condition, and for that we have to change the energy of the electrons, in fact the velocity of the electrons. But since we have a scanning electron microscope source here, so it's very easy to change the energy, and once we change the energy, we change the velocity. Thus the synchronicity condition is not satisfied, and as expected we see a diminishing of the maximum acceleration gradient that we can get. So all seems fine. In 2016 we've already shown 200 mega electron volts per meter acceleration gradient, and we expect to publish even larger results soon. And note that all of this is done with sub-relativistic electrons, so beta equals 0.3, which is roughly 30 kilo electron volts. At around the same time, in 2013, another group in Stanford was pursuing the same idea. Instead of using a single-sided grating, they use a double-sided grating in a symmetric fashion as seen here. The electron beam goes through the grating itself, well, the channel itself, while an 800 nanometer laser pulse goes through bulk material and into the channel to produce the near fields. Now, the electron source from SLAC is a 60 MeV electrons with 1 picosecond Planck length, and I'm only mentioning these numbers because I want you to notice that the laser's period is roughly 3 femtoseconds as opposed to this 1 picosecond, and that means that we don't just get net acceleration or net deceleration. In fact, we get some kind of smearing of the spectrum. You can see this here in these measurements. So here we have the energy gain when the laser is off, and here the energy gain when the laser is on. So you can see that some electrons have been accelerated, some have been decelerated, and this is the spectrum with laser on as opposed to laser off. Now, if you look only here at the high tail of accelerated electrons, then you can still deduce a acceleration gradient of roughly 300 mega electromoles per meter. Now, these two proof of concept experiments were the motivation to the founding of HIP, the Accelerator on a Chip International Program, which is very generously funded by the Gordon Betty Moore Foundation. But certainly not only these two groups are part of this collaboration. We have lots of support in simulations from TechX by Ben Cohen and from TU Darmstadt by postdoc Uwe Niedermeyer. We have a collaboration with large facilities in SLAC, DAISY, and PSI. In terms of laser sources and coupling into the DLA structure, we have groups from Vukovic and the fan group from Stanford who work with us. In DAISY, we have the Hartel and Kotner groups. And in terms of future applications for this accelerator in a shoebox, we have colleagues from PSI, SLAC, and Tsinghua University. And we really need everyone here because producing an accelerator in a shoebox is not an easy task. There are many, many ingredients that we have to take into account, characterize every one of them, and then somehow put them all together in a shoebox. The first thing that we have to take into account is our electron source. So in large facilities, they mostly use flat photocatalysts, which produce many, many electrons. But here, don't forget that because this is a near field effect, our channel is very small in the order of a few hundred nanometers, and we have to fit all these electrons in. If they're out of it, they won't be accelerated. So this is the first thing that we do, and we're going to opt for electron sources as nanotubes, which I'll explain soon. Of course, our main concern is to accelerate as much as possible with the least amount of the least length. So the acceleration structures are very important to us. Once we do that, we can think about other things like deflecting or doing multistage acceleration, gating, streaking, all kinds of auxiliary things we can do with these electrons. And an important issue with the electrons is that we have to keep them in this very small channel, so confinement is an issue. And lastly, like I said earlier, we have to somehow couple laser light into the electric structure such that every pulse arrives at the right time and the right polarization and for the right amount of time to have the electrons experience acceleration. So I'd like to start with a very short touch on electron sources. In principle, for the emission mechanisms, in particular metal vacuum, in a metal vacuum interface can be described by the Keldysh theory. And I perhaps could differentiate between four kinds of interactions. The first one would be a single photon excitation, where we have about one photon that is enough to get the electron from metal to tunnel through the barrier. In the second one, multi-photon excitations, we have enough photons such that this electron can just barely escape the barrier and emit. In the third one, we have so many photons that we don't just get electron emission, but with some kinetic energy. And the last one, the optical field emission or field-induced tunneling, this is the strong field regime. The optical field is so strong that we're actually bending much the barrier, and the electrons can directly tunnel through to vacuum. Now, in the group of Peter Homelov, what we mainly look for or work with are these tungsten nanotubes, which the group specializes in. So this could be treated as a zero-dimensional system, a nanotube. The radius here, right at the apex, is roughly 10 nanometers. And we can see from these simulations that we can get near field enhancement of roughly 3 and practically up to 6. And this is the field enhancement, not the field squared enhancement. So this gives us large fields with moderate laser intensities, which allows us to rip out electrons with high brightness and low emittance, where in accelerator physics, high brightness means we have many, many electrons over low emittance, which is very, very small and compact space. Good. So the thing is with these nanotubes is that even though they're already used in some groups around the world, they're not fully characterized. And the first thing that in our group we wanted to do is to find out if these are also spatially coherent, as in the case of DC mode or field emission. So in field emission, we use some amount of DC voltage on the tip, and we bend this barrier a bit so we can get electron emission. But we really want to trigger it so we know where our pulse is and when it's emitted and where it is in space at all times. So the first thing that we did is look at DC emission, and we know it's coherent. Now we want to check the laser-triggered emission. To do this, what we do is we generate photons at the tip, or we send them to the tip, with just high enough energy to overcome here this barrier or tunnel right through it. This is important because then we get electrons that have a relatively small statistical spread. Okay? No? Should I just go on?
Try turning off the microphone.
Okay. I can talk loudly. So, we have photons now interacting with this nanotip, and that emits electrons. And the electrons go through or just around an electron beam filter, which is in fact just a carbon nanotube. And just like a holographic experiment in light optics, what we get is fringes at the far field. From these fringes, we can tell if this is rather more coherent or less coherent. So in DC mode and in laser-triggered mode, we see more or less the same thing. Qualitatively, good. It looks like we preserve coherence. If we really want to quantify it, we could just start counting these fringes and check their contrast. And yes, we see that they're more or less the same. That means that we have a good source for electrons, for laser-triggered electron emission, using near UV pulses with the laser on the tip, such that it is almost as specially coherent as a DC field emission. I'm saying almost because there's very small change, but it's well enough for our application of the electric laser acceleration. Okay, so now let's move on to the important part of acceleration structures. Let's recap on what I said a few slides ago. So in 2013, we had a single-side grating, in which we showed for subrelativistic electrons 25 mega electron volts per meter. In the Stanford group, they used a double-sided grating, in which they showed 300 mega electron volts per meter for relativistic electrons. But these days, what we mainly follow is the dual pillar grating, which was introduced. It was called a colonnade in Robert Palmer's 1986 paper. And the good thing about this is that the driving laser now doesn't have to go through all this bulk material inducing all kinds of nonlinear effects. The fabrication recipe is relatively simple. One day in the clean room should be enough. And there is no need for any special alignment, because here you have to bond these two wafers together with sub-micron precision, which is not an easy task at all. So with this, we can go on to this example from the Stanford group. Here you can see two lasers coupling from left and right in a kind of dual drive fashion. The lasers are 2 micron with 300 femtosecond pulses from each side. This whole thing sits on a mesa which is roughly 3 micron wide and 75 micron tall. This is so we'll have optical access directly to these pillars. The pillars are roughly 3 micron high with roughly 1 micron period and 15 micron length in total. They're slightly elliptic, which you can't really see here, but this is done following optimization. With these two dual drive beams, we can have some relative phase between them, and then we can control the profile, the electric field profile in the channel. So for example, if the relative phase is 0, which is what you see here, then you get a kind of a cosine hyperbolic mode here. And if you have an inverted phase, then you have this sine hyperbolic profile along our channel in this direction. Now, the derivation of these modes is relatively straightforward, but it's lengthy, so I'll skip it. And we'll just try and look at the results. So the first thing that we assume, we have a TM field in the channel here. And this is how it would look like. You have the two coefficients of excitation from left and right, C1n and C2n. And you can see that the evanescent fields here in the middle along Y, right, have a decay length of gamma. Now, gamma could be related through the synchronicity condition to the laser's wavelength and to the velocity of the electron. And again, as I said earlier, is in the order of a few hundred nanometers. Now, we can take this, plug it into the Lorentz force, which is what interests us in terms of acceleration or forces on the electron, and rewrite it a bit differently, such that we have these three components in the Lorentz force. The first one is out of plane deflection, so that's Fx, up or down. It's 0 because we assume that these pillars are infinite and you're using a plane wave. We also have deflection in plane, so that's along Y. So we could have the electron crash into the pillars or focus to the central axis. And lastly, we have acceleration or deceleration in Fz, depending, of course, on where the electron is relative to the phase of the light beam and the near field. Now, you'll notice that here we have reformulated C1 and C2 into CS and CC. So by controlling these two, we could have either in the channel a pure cosine hyperbolic field or a pure sine hyperbolic field. This is depending if we want some kind of symmetry or we want to skew the beam for some other applications. The more interesting thing here to note is that Fy, the in-plane deflection, is always 90 degrees out of phase with Fz, which could be the potential acceleration part. And this depends on phi, which is this here. And again, depends on the electron velocity, the injection phase, the laser's phase, and so on. So more or less, we would always like it to accelerate. But sometimes we'll also get a mixture of deflection, in-plane deflection, in and out. And that's a problem that we have to deal with later. In Erlangen, the setup is perhaps just a bit less complicated. What we have here is not a dual drive system, but for example, we start with the scanning electron microscope source. So it's a Schottky emitter. We excite it with a UV laser pulse. So we get here a pulse of electrons, roughly 100 femtoseconds in length. These are 30 keV electrons. The electrons go through the channel between the pillars, while at the same time we have a 2-micron laser impinging on the pillars from this side. The laser pulse then goes through the pillars and is mirrored by this Bragg mirror up here to create a more or less symmetric or asymmetric, depending on the structure here and the differences. And then these electrons experience, hopefully, acceleration. Once they pass through, they're bent by a magnetic spectrometer, read out on the screen. And on the screen, what we usually see is this kind of picture. Well, after some, we see a picture, a 2D picture, but we can find this one from it. Without laser, we see just the central wavelength or central energy of the electrons. With the laser on, we see two features. First, this high peak diminished a bit. We'd expect to have it diminished all the way down, but this could happen, for example, if the IR laser is not longer in length than the electron pulse. So some electrons didn't interact, they're still here. And then we get this energy modulation, which I mentioned before, and I'll touch on again in a couple of slides. Let's look first at our structure more carefully. So what we have here is, first of all, I remind you that we're using subrelativistic electrons. So the dimensions here are smaller than the one they use in Stanford. The pillar period here is roughly 660 nanometers. The mirror spacing for the Bragg grating is roughly half a micron. These mirror plates are about 144 nanometers in width. And this aperture thickness, that is this channel here, is 225 nanometers more or less, with our pillar 3 micron high. The Bragg mirror is fabricated in the usual fashion. So we have stacked layers of alternating refractive indices. In this case, we have silicon, vacuum, silicon, vacuum. Each layer's thickness is lambda over 4n, where n is about 3.45 for silicon. And this means this large contrast between vacuum and 3.45 means that we really don't need any more than 4 layers to get optimally high reflectivity around 97, 99%. Now, in Erlangen, we checked what happens if we use only a single side drive or using this Bragg mirror. And already we see that we have the field enhanced in the channel by measuring our acceleration or modulation of the spectra of the electrons. And we can see an increase in about 50% when we do use the Bragg mirror, which I would say makes sense. But I promised the thing about the electron having energy modulation instead of net acceleration. So don't forget we have the laser coming from here and then being reflected by the Bragg mirror. The laser has enough pulse length, so about 650 femtoseconds, just that we don't really see it coming and then returning. It's more like of a steady state situation, especially when the electron gets here. And here I'm going to show you just one electron. And what you can see with the color code here, you can see the phase. So here we have positive and here we have negative. But the more important part is here. So this is one unit cell. We have here pillars, pillars, pillars. And this simulates an electron that is obeying the synchronicity condition and is injected exactly at the right time, such that it experiences the most acceleration possible. In other words, this is the synchronous particle. So you can see that if you follow this electron and the color code, it always experiences positive from 0 to 2 fields, and that means it always accelerates. If I had another such electron trailing just a bit behind, then it would experience some acceleration and some deceleration. And if I had one more electron exactly half a cycle apart, then it would be only net decelerated. And this is the reason that we get this energy modulation. In fact, if we look again at our system, and let's suppose that we have a UV pulse that emits from the tip an electron pulse with roughly 100 femtoseconds, and this interacts with, let's suppose, an IR laser pulse with roughly 100 femtoseconds. What you really should look at is what happens in the phase inside this pulse. So we have supposedly many electrons that are distributed all around, and each of them is experiencing a different phase. And I hope now I convince you why we have this kind of energy modulation in our measurements. Of course, in order to solve this, we have to think about a way to have all these electrons experience more or less the same phase and more or less, hopefully, the same field, so that they can all accelerate and not decelerate. This can be done with what we call suboptical bunching or compression, but this I'll maybe touch on at the end of the talk. Let's go on to some idea of how to use deflection. So now we have enough tools to understand what's going on in these kind of accelerating structures, and see if we can have some auxiliary elements, not just only deflection. So in the single grating analysis, if there is an electron here going on the grating, and it's aligned with the grating vector and with a TM polarized beam, then we will have in the Lorentz components one, like I said, component up or down. So we'll have the electron going away from the grating, for example, out of plane deflection, and potential acceleration. I'm only saying potential because it depends where it is relative to the phase of light. Generally, though, this electron has some angle with the grating direction and also with laser polarization. So we will also have some additional in-plane deflection along Z. It's not too bad because maybe we can use it to our advantage, right? Let's think about something like this. Using deflection, we can have perhaps an optically driven accelerating electron lens. So this is the setup, and we have the electron going here to some grating that looks a bit parabolic in shape. And our initial energy is roughly 29 kilo electron volts. And the electron beam is very, very small relative to 2.5 microns. So we can treat it as an array of electrons that we can scan along X. And these electrons go through the grating, so they're accelerated, but also deflected towards the symmetry axis. Once they pass through the structure, they have some energy modulation. So in our experiment, it was roughly plus minus 0.6 kilo electron volts over this initial energy. And then we have a knife edge scan that gives us some special information, and a high-pass energy filtering spectrometer, which gives us energy information. OK, so what do we get? We have, using the knife edge, we can measure the centroid on this MCP here. And we see here the centroids for different measurements. We see linear slopes, so this implies some thin lens behavior. So we have a thin lens for electrons. But we have also energy modulation, or in this case, since we're filtering, we only can take some part of this spectra. And we see that we have acceleration. So different slopes give us, because we have different slopes, we in fact have a chromatic lens. So for different energies, we get a different slope. Higher energy electrons, here you can see that they deflect less, and you can think of this as because of perhaps the momentum of the electrons is too large, then we don't get the exact behavior for all of these electrons. There are some other reasons, but we can stop here. So I'm going to touch with deflection a bit more later, but first let's think about multistage acceleration, gating, and streaking. Because if we really want to reach high energy electrons, just one such interaction over a few microns is not going to be enough. So as a proof of principle, what we could do is have two interaction regions, for example. So we have one laser pulse here and one laser pulse here. We can control the phase between these, or the delay between these two pulses when they arrive, with subcycle precision using a delay stage in one of the arms of this interferometer. And what we get eventually is that we can, in the first interaction region, accelerate the electrons, and then in the second interaction region, choose whether we want to suppress this acceleration or we want it to accelerate even further. And in our measurements, we use, don't forget, a high-pass filter. So we, first of all, only look at those electrons that have been accelerated. And we can see that our count rate changes with the phase difference between these two interaction points. So here we have acceleration, and here we have no more acceleration, and so on and so forth. If we plot this energy gain versus the fraction of accelerated electrons, then now we can see that if we only have one interaction region or the other, then we get acceleration to some value, green or blue here. If we operate them constructively, we have here about double the acceleration. And if we operate them destructively, then there's almost no acceleration at all. So this is expected because this is a linear system, but we can also use this for example, an idea of all optical gating. So here you can see that we can control using this high-pass filter whether we have electrons or not, and this can be controlled with some femtosecond precision. In this kind of experiment, we can differentiate between two time scales. The first one being the laser period here on the left. So this is more or less the same image that we saw before. And here we can look at the envelope of the whole pulse. And of course, once we look at electrons that gain more and more energy, this envelope is going to be shorter and shorter. In principle, what we could do is have one of these pulses very, very short, and then we can effectively choose only or yield only one electron pulse. So we have a bunch, could be attosecond electron pulse going through the system, and then we can use it to probe some other system with high precision in time. This brings about the idea of streaking. So streaking is, in fact, when we convert the time domain to spatial domain. So in principle, we require about 1/4 of the optical cycle because we want to sample the more or less linear part of the sine. And in this case, in this kind of idea for a system, we could still have these two laser interaction spots, which would give us gating, just like before. This tilted grating that I mentioned before with deflection would give us this conversion from time to the spatial domain, and we could use the knife edge and the energy filter for analysis. This perhaps is a too complicated system. In a schematic or generalized view, what we really need is just this tilted grating. Our laser pulse doesn't matter exactly what's the length of this pulse. We could think about an electron bunch which is subcycle, and then we'll get this kind of streaking phenomena and use it for measurement. Okay. So in the time I have left, I want to address the last two issues or difficulties that we're working with to solve. One is confinement of electrons. So you're now experts in deflection, and you know that the electrons don't only accelerate at the same time they might be deflected, and we want to confine them into the channel. And lastly, the very important problem of how to get all this laser light into our DLA structure, not just one stage, but for multiple stages. So there is a problem of transverse deflection. I showed you earlier that well, we have this phi phase. So any deviation from phi equals, for example, depending on your derivation from pi over 2, these electrons won't be synchronous, and then they won't only have acceleration, but some deflection also. So we could think about perhaps taking some solenoid or some other kind of instrument element from accelerator physics and then just keep the electrons in the channel. But don't forget that with optical fields, we're talking about several gigavolts or at least 1 gigavolt per meter field strength. You can't compensate for this with conventional elements such as quadrupoles, solenoids, Einzel lasers, etc. So what we really need to do is think about how can we solve this perhaps with optical means. This is, again, something I showed earlier, and this is what I said earlier about phi. So phi, again, depends on the electron velocity, the laser's wavelength, and the period. And we usually would like to work at around phi equals pi over 2, because then here we have net acceleration. But there can be only perhaps one electron there. We have a pulse of electrons. So some of them will always feel some kind of deflection force towards the pillars or away from it. If you think about an electron beam, then this means that this beam can be focused or defocused. And the point is, what we really want to do is try to flip this phase when the electron beam starts defocusing too much that it would crash into the pillars. So in essence, what we want to do is engineer the DLA structures. There's a method called alternate phase focusing from accelerator physics from 1956, and we borrowed this method. And in a nutshell, the idea is that once the electron beam begins to defocus, all we have to do is, like I said earlier, flip the phase of light, or using the structure, of course. With just a laser beam, it would be hard because we want the near field. And then we turn focusing forces to defocusing forces and vice versa. If we alternate between these two, so this is an interesting result from accelerator physics. So we have to, because there's conservation law, essentially, then what we want to do is, once it defocuses, we want to flip the phase. We're going to have to stretch it in some other dimension. So in this case, what we could do is flip between the transverse and the longitudinal dimensions. So effectively, what we could get is actually bunching of these electrons. So this is the first problem I told you before. So a structure like this could, in principle, not only start flipping between the focusing and focusing forces for this electron beam, and then the electron won't be lost crashing into the walls, but also start to bunch the beam itself. So this is the effect that we want in order to get net acceleration throughout the structure. You can see that we have some macro periods here, where every so often we have a drift space. This is exactly for flipping the phase. Now, you can think of this maybe as a problem from textbooks in optics, where you have focusing and defocusing lenses, and then you get some kind of a waveguide. This is the same idea. You're using first-order effects, which effectively give you a second-order focusing of the beam. OK, and the last part of this talk is about a way to get our laser light into the structures, because everything I've said so far was free space to a nanostructure. Eventually, we won't have just 15 microns or so. We could have about 1 millimeter should be enough for our proposal. But we need to get somehow this laser synchronized between the tip and every one of these stages. So the way to do it could be perhaps, thanks to our colleagues in Stanford, use this kind of scheme. So what we have here is a dielectric waveguide network that is fed by these input couplers on silicon, for example. And every so often we have here, for example, optical phase shifters. We have pulse delays to match the electron's velocity. And the electrons go through here. This is the dual pillar structure. And of course, everything has to fit together such that these pulses get through this whole network and exactly at the right time to where the electron should be in the channel. So this is a schematic kind of view. You may ask, how can we implement these kinds of optical phase shifters and so on? So here's one example. This is inverse design and demonstration of a compact and broadband on-chip wavelength demultiplexer from the Vukovic group in Stanford. And this is a very nice idea from them, where they say, OK, we don't really know how to solve this, or maybe we could, but let's just let an algorithm do it for us. So they designed this algorithm where as an input you have laser wavelengths of 1.3 microns and 1.55 microns. And there's just black box, or in this case, the white box, and 2 output channels. And they feed their algorithm these kinds of initial conditions and tell it that all they want to do is split these 2 between the channels. So the algorithm computes what it has to do. It gives us the amplitude and the phase of this kind of structure according to Maxwell's equations. Then they binarize it and they optimize it so it can be easily fabricable in a clean room. And this is the result in silicon. And what you have here is, in fact, the realization of what they've done here. And it's not limited, of course, to just wavelength demultiplexing. We can think about such an algorithm to give us what I said before, either delay or phase shifting and so on for our application. So these are many people from the HIP collaboration in a meeting we had in 2016. I'd like to thank them all, and especially our group in VU Erlangen, the Peter Homloff's group. These are the persons in our DLA team. And of course, our funding from the Gordon and Betty Moore Foundation, ERC, and BMBF. And with that, I would like to thank you and welcome any questions.